Hello and welcome to class 20 in this lecture series on integration theory. So today we're going to do, this is actually my least favorite class in this whole book. So kind of a standalone topic in 6.1, which is about differentiation of measures, is the change of variable formula, which doesn't really fit there. It's just, I guess, Cole needed somewhere to put it, so he put it there. But you know, you know, or you should know by now, the change of variable formula. But it's very tedious to do the proof properly, and most likely you haven't seen a proper proof of it. So it's my unfortunate role here to outline such a proof. The book does it over in a sequence of lemmas and results, and you know, it takes time to do it properly. Anyways, let's get going. So the formula, I hope you know it. Here's a set U. Here's some other set V. And they are open, and then you have a function here, which I can call U with a dash on it, so to signify that I go from RD into RD. Right, and then let's say you have some function here f that lives on V. So here's the real line, and we have a function f there. So if we want to integrate, well, we're interested in the integral of f over the set V, the lambda, the Lebesgue measure. So what happens here? Okay, so now we want to evaluate this as an integral over U. For whatever reasons, there are many. Yeah, anyways, it's not time and place to motivate why we need such a formula. So let's just say we need it. So we can pull back this function f through U. So now we have a function that lives on U. Let's say that here are the variables, we call them y. Here we call the variables x. If you want to be a bit specific, we can write here y and lambda parenthesis y. But then we know that when we pull back things, size changes, so we need some factor to account for this. In the one-dimensional case, it's just the derivative. And in the several variable case, it's what's called the Jacobian, which basically, okay, so what it is the derivative of this function U at some point here, x. You know, with the multivariable Taylor formula, this gives you, like, if you have some perturbations, you look at x plus h, then you have some point here in the vicinity of x. How is this transformed? Well, it gets to the point here, u of x plus u prime of x times h, right? Where u prime is now a matrix, yeah? So some vector here plus some higher order terms, which are order yada yada. So it's still the case that it's the derivative of u that somehow tells us how size changed. Anyway, this is a matrix, it's a square matrix, like d by d, right? So we can take the determinant of that, and for some reason, which I'm about to explain, this can be positive or negative, but the size of that number, so the modulus, gives the relative change in size here. Then this is change of variable formula. Maybe I should have a bar on the x's as well. Let's just skip all the bars. We're in multi-dimensional spaces, and then we just know that we're not putting, this is not kindergarten any longer, so we don't put any bars any longer to show that we're dealing with vector stuff. Okay, so before I tell you the details of the proof and the constructions, we of course need to discuss for what things it holds. And already here, there's much more than meets the eye. So okay, we have these two u and v. and we have a small function u here. So this guy and that guy should be open, okay? And u should be a C1 bijections, meaning that it has a derivative, is differentiable at all points, and the partial derivatives are C1 functions, so they are continuous functions, right? In the book, they also assume that the inverse, so this is a bijection, and it has an inverse, right? There exists a function doing this, and the book assumes that the inverse is also C1. That's not necessary, because if you know the inverse function theory, that theory will give you that this function has is differentiable with continuous derivatives if u is. Okay. What does it mean for a function to be C1 in several variables? Well, if we have one function, okay, so if we just have one function, it's this. So from several variables to one variable. X plus h, you have the perturbation minus the value at the point. The value of this is the sum of the partial derivatives times hk plus ordo norm of h. Yeah, so the modulus, the norm of h, when this means that if I take this minus that in size divided by the norm of h goes to 0 as h goes to 0 in several variables. That means like, okay, take a small disk around 0 and look at the supremum of the division of this minus that divided by norm of h, then that's less than epsilon. So given epsilon, you can find a small disk, so that's true. Okay, that's for one variable. Now, if we fill up here, so you get d functions, just write the same formula again. Right, and then it looks like this. But now this becomes very big. Yeah, so, okay, then we start looking at this right-hand side. You should know it by now. I mean, this is the matrix U prime, evaluated at x. This is implicit here that we evaluate at x. This is matrix vector multiplication. And then we just write plus ordo h, where now ordo is like a vector ordo. Okay. And then here on this side, we just write u of x plus h minus u of x equals to, so this is like now vectors. Yeah, so then we compress the notation. Note now that this is just a fixed matrix at the point x, right? So there's another way in Banach spaces, you can also introduce differentiability. So if u and v are some infinite dimensional spaces. And then the way you go on about it is you say that, okay, u is differentiable at the point x with derivative L, where L is a linear operator from the space u to v. If you have this, so limit as norm of h goes to 0 of this quotient is 0. Okay, so that's equivalent with saying that, well, this division here, another way of writing that, right, there is ordo h, right? So this is basically the definition of ordo now in this higher dimensional setting. Okay, so this is Frege differentiability if you want. This is infinite dimensional spaces, but now it's not infinite dimensional spaces. So to go back to our finite dimensional setting, there's only one unique. So linear operators in finite dimensional spaces, just matrix multiplication. And it's easy to see that this defines this linear operator uniquely, and it becomes this matrix here, right? That we get from just sticking in the partial derivatives in a square scheme. Right, so this is what we're going to require from our function u. So this is going to hold at every point x, and u prime as a function of x is going to move continuously. Okay, then it's C1. Unfortunately, there's much more to this than meets the eye still that I have to explain for you to not get lost in the proof. And one thing is has to do with this norm here. What do we mean by the norm in RD? So usually, by the norm, we mean the one we get from Pythagoras theory, right? But that's not the only norm. So actually, RD is we can think of that as an LP space as well, right? So there are all the P norms, which you get by replacing the 2 here and the square root with 1 over P and P. Okay, so we have the L1 norm and so on. And in fact, in particular, we have also the L infinity norm. So there's alternatives here. Okay, so in the infinity norm, that's just the maximum of the different HKs. Now, all norms in finite dimensional spaces are equivalent in the sense that we can bound one by some constant times the other always. And here we see that, okay, first of all, what are the unit balls here with respect to these norms? So if I look at the set of all x, such that norm in the 2 norm, the norm is less than 1, well, I just get a circle, right, in 2 variables. If I do the same with the infinity norm, I'm getting a square. And so in terms of topology, these are also equivalent because you can always fit a square inside a circle, which you can fit into a little bit bigger square. So if you think of what means open, what means closed, and all of these things, it doesn't matter which one you use. So in fact, I mean, this norm is always bigger than the value of the maximum element, right? Because if you just throw away all the other ones, and you keep the maximum one, this thing here is just the modulus of the maximum 1. So we do have this chain of inequalities where this one I have the square root of d. If we replace in this formula all elements with one with the biggest modulus, then you get this. All right. So in terms of order notation, this limit here, it doesn't matter which one we use. But for our computations, we need to know a bit more about the size of this constant or how fast this goes to 0. And then if you want concrete estimates, of course, then it matters if we work with this one or if we work with this one. And unfortunately, we're going to work with this one because it's possible to not work with that one, but then we have to play with these inequalities all the time and it gets tedious. So it's actually better, you get a nicer proof, you just jump in the cold water and reshuffle your mind to work with this one to begin with. And it's kind of clear why, right? Because doing Lebesgue measure is intrinsically connected with cubes, not with round things. So if the unit ball, so to speak, is already a cube, then it's easier to handle. Okay. The problem is now, all right, so we have also the concept of the norm of a matrix. So if I want to look at, for example, u prime of x, or just any matrix A, but okay, now we take this. What do? I do the supremo, u prime of x. I apply it to some h, and I divide with the norm of h. I take the norm up here. That's the definition of the matrix norm. But of course, here it's also, if I take the 2, which is the usual one that you probably have seen before, then this here becomes, well, it's not very, if it's a self-adjoint and it's the biggest eigenvalue, if it's not self-adjoint matrix, then it's not really clear to connect them with the eigenvalues. So this is sort of a fishy object, all right? That there's no closed formula for how to compute it in general. If I put infinity here, I get something else. And And that's the one we're going to use now. Now, if you think about it, with this norm, this becomes kind of easy, because if you want to look at what's the the infinity norm here, you just have to find the largest value, right? And the same down here. So if you look in, so what is matrix multiplication times h? Well, it's basically this summation formula here, right? So you look for the one which has the biggest value. Okay, so let's look at this first row here. Let's say the maximum, the supremum is obtained for the first row. What's that supremum going to be? Well, downstairs we're going to have the biggest value of h, and upstairs we're going to have. All right, so even that wasn't so trivial, but okay. Once one of the hk's is big, let's say it's 1, it doesn't hurt to let the other ones be 1 in modulus as well, because that doesn't affect this norm, right? So they're all going to be maxed out. And then we want this sum here to be as big as possible. Now, if these are complex numbers, you get that by just choosing a direction space with the first one, let's say, and then choosing the angle here so that you always like go further in that direction in your sum, right? If you're on the real line, this just means you want to choose your hk so that the sign always becomes the same. And then this sum here will become, if you do that, it's become the sum of the u1 dk, the xk in modulus times your hk, right? And if they're all having the same size, then you get here this, and then you divide that one out. So you see that this division here actually becomes this sum. And that happens for every row. So if you do the infinity norm, what you need to do is you need to do the max of I. This is I, and then the summing over k. Okay? So this is what we get. All right, now why is this important? Because as I said, we want to know how big this is or how much it can deviate in a neighborhood of a point, right? So it's not good enough to just know that it's small, like this notation entails. Okay, so to understand this final step, let's just remember from one variable. So you have a function b, and I want to look at that at x plus h minus b of x, and let's not involve the derivative at this point. What I do then, well, remember this is a mean value theory, right? So there exists some point between x plus h and x, such that this was, right? So theta is a number now between 0 and 1. Okay, this exists in one variable. In several variables, this becomes a bit more messy. But with this norm, the infinity norm, we can treat multivariable. I mean, we just have to look at what happens in each row individually, right, to figure out this norm. So, okay, if now our function is, this v is u1, then the derivative here, evaluated at x plus theta h, is just, okay, so then we don't have this term, it's just this, but instead of evaluating at x here, we are at some other point. Okay, so then I get here, so the modulus of this, I can estimate it with this, right? Times, then again, let me put him back, I erased him before. Okay, so this is the norm of this matrix, but evaluated at some nearby point, gives an upper bound to how big this can be, yeah, in the modulus, yeah, so if I'm interested in estimating, the modulus there. Okay, so this means then, if you think a bit about it, that if you have some number c such that your derivative is less than that value c for all h with, let's say, the norm less than whatever, some delta, then, okay, then I just get C times H infinity here, right? So we get this formula. Okay, and that's true for any U, okay? Well, yeah, let me change this to a function V, okay, but now V is multivariable too. Here's the nice trick that we're going to use. So now, sorry, my backboard is getting really out of space, but now if we apply this to the function V of H, okay, so U of X plus H minus U of X minus U prime of X times H, then my V prime is going to be U prime, okay, at H, then it is this, yes? So now I get the formula that U of X plus H minus U of X minus U prime of X times H in norm divided with H is less than or equal to the supremum U prime of Y minus U prime of X in the operator norm, or this norm here, right? For all Y's such that the norm of X minus Y is less than delta. Okay, so this, yeah. If H is less than delta in norm, then this supremum here dominates this. So this gives us, right, so if U prime now is C1, then I know that if delta is small enough, this is going to be below some epsilon, at least if the point X is fixed. So this gives me a way of quantifying how big is this. As I said up here, we don't just need to know that the limit is 0, we need to know how that we need to control this, and this is the way we're gonna control it. Fine. Right, back to now change of variable formula. So in this lecture, because this gets enormously long, I'll just explain you basically 613, I think it is. Yeah, about size and the linear change of variable in RD, and also just give you a bit of intuition about how this, why the change of variable formula holds. That's all for today. So if you feel like it, you can just read 613 in the book and move on to the next lecture at this point. Yeah. Okay, so basically what happens here, if we take a small square around this point, okay, let the point be here, and then I put it in the lower left corner, it's easier like that. So this is my point. Now this is going to turn into some sort of rhomb-like shape here, where this matrix kind of tells you what are the side vectors here. Yeah. So this little rectangle here is usually small. Yeah. You need to, at some point, we're going to chop up this region U in many small rectangles. But to first understand how matrices transform size, it's enough to assume that this guy here is the unit cube. Yeah. So we have this, and now we ask the question, so instead of writing U prime all the time, I'm going to have some general matrix, and I'm going to call that general matrix T. So T is now just a fixed matrix, okay? Or did I call it something else here? A. Should not be T, it should be A. So what's the size of A when you apply it to the unit Q? So if we can answer this question, then we can get to this question easily by, I mean, any small rectangular or higher dimensional box. You know, so the measure in each dimension, you can pull. I mean, if this has length 0.1, then you can pull that outside and replace it with an interval from 0 to 1 instead of from 0 to 0.1. So its size is naturally linear in each dimension, respectively. So if we know what size this gives, then by just multiplying by the side lengths, we can easily get the size of A applied to a higher dimensional box with any sort of side length. Okay, so we have to understand this, and that's not well explained in many books. So this is not actually integration theory. This is linear algebra. But out of benevolence, I will explain it to you anyways. And of course, the answer is that this is equal to the determinant of A in modulus, right? So that's where this comes from. Question is, why is it like that? Well, so we want to establish this formula. Okay, let's first understand this. So the matrix A has A1, A2, dot, 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 AN. These are the columns, yeah? And if you look at them, you just multiply with a vector x here, whose coordinates are between 0 and 1. So basically, you get all possible linear combinations of these with the coefficients are between 0 and 1. So if this is A1, this is A2, then in 2 dimensions, you would get this rhomb, right? And yeah, then if you have 3 dimensions, and here is your A3, then you get, this is hard to paint, oops, something like that. You get the corresponding like skewed box, yeah? So that's what we're going for. So this is like the parallelepiped, I think it's called properly. Parallelepiped spanned by A1 up to AN. That's the volume we're interested in. Now, first, so anytime you deal with linear algebra, you want to choose a basis where your matrix A becomes simple. Yeah, I mean, so usually, okay, I don't know how much of linear algebra I should assume you know. The best change of basis you can do is by a unitary matrix, right? So then you keep all, you don't change angles, you don't change nothing. It's like a rotation in space. But no, we don't need that. We can work here with more general changes of basis. So the point is now that this guy, he will not see whatever basis you do. So instead of thinking of A as a matrix, we think of it as a collection of column vectors. Yeah. So now we just have n vectors, or like d vectors it should be. I have d vectors in Rd, and I want to know the size of this thing, yeah, in Rd. So then, so the determinant, so if you have some transformation, some change of variable given by a matrix T, so technically that can be just any invertible matrix. Then to express the matrix A in a new basis where the column vectors of T are the new basis, do this. Yeah, this we learn in linear algebra. And now if I do a determinant on that, now the determinant is multiplicative. We have this formula, which we also learn in linear algebra. And now I can multiply this guy with that guy, put them together, and then you get t minus 1 times t. That's the identity matrix. The determinant of the identity matrix is equal to 1. So at the end of the day, I just get the determinant of A here, right? So this means that if we want to evaluate this formula, or yeah, we can do it in any given basis. So how can we choose a smart basis where we so unit, okay, where we can kind of see what is the volume of this thing. All right, so here I'm adding some stuff I didn't say the first time, so there would be a bit of jumps. So of course, the way we measure size in Rn is using the Lebesgue measure, right? So before I do an argument based on changing basis, we need to know that that doesn't change the Lebesgue measure of the size of things, right? So basically, if I have some basis, right, or I have the standard basis, this is E1, E2, E3, right, and then I take some other basis, which is orthonormal, yeah, and then this is T1, T2, T3, so these are unit lengths and with 90-degree angles between each other, and then T is the matrix here, which is then becomes unitary. Then to express a point here in this coordinate system X in this one, the corresponding coordinates for X in here, this becomes, you know, the point doesn't move, so he's still here. So what are the coordinates for that is given by T star X, because, well, unitary matrices have the capacity property that the inverse and the adjoint is the same thing. But anyways, let's maybe stick to that. So this is the coordinates now in the new system. So basically what I need to know is that if I take a set A here, and then this gets transformed to T minus 1. Oh, A was a bad notation because that's our matrix. But S then, I need to know, before I do this argument, that lambda of S is equal to lambda T minus 1 of S. So this change of basis doesn't change the size of things. Now that's an exercise 1.4.10 or something, which relies on the proposition 1.4.5, which says that Lebesgue measure is unique. It's the unique translation invariant measure that gives the unit cube the size 1. All right. So clearly, I can define this as a new measure, right? Mu of S. And now it becomes translation invariant. Yeah, because if I, you know, add, because this guy is translation invariant and this is a linear operator, so it's translation invariant here as well. So if I add the point, do plus the set S plus the point A, then the measure doesn't change. Okay, so this is a translation invariant measure, and then we just need to check that the unit Q has size 1, then proposition 1.4.1 tells us that this identity holds. How do we know that the unit cube, all right, so this box here becomes, has size 1, you know, in this coordinate system, so the Lebesgue measure now this, you know, if we straighten this up, now what I did is I kind of rotated my cube, right? So now it stands up like this. And intuitively, if we think of this as just like a rigid rotation, of course the size doesn't change. But that's exactly what we're about to prove. So how can I actually prove that this has not changed the Lebesgue measure? Well, after all, I mean, n dimensions, or maybe d dimensions, yeah, or d, I think, yeah. It becomes hard. I mean, technically, I need to start covering it with small cubes that are parallel with the coordinate axis, right? Which in my new system is T1, T2, and so on. And then show that, you know, then I get some problem here along the edges and whatever. It becomes messy. I don't see a smooth proof around this silly thing to check that this has volume or Lebesgue measure 1. How would I actually prove that? Well, so here's the deal. Arguments that provide intuition are rarely the shortest ones. So I'm trying to give you arguments here that provide intuition. In the book, there is a proof of the, what we're trying to establish here, basically that lambda of t of unit cube or some other set is equal to the modulus determinant of t times Lebesgue measure of that set, in this case the unit cube. And this is what we need now. So we can prove that without doing this change of basis argument. Yeah, there's a proof in the book based on induction, but you don't get a feeling for it. So another way to prove this formula, assuming we know the change of variable formula, is to actually use the change of variable formula, right? So here's our u, here's our v. So let v be equal to t of the unit cube. And then u be equal to the unit cube. And we're going to repaint them, right? So if we do this technical dry proof of the change of variable formula, then you see that the integral over t of, okay, let's say any set S, and then integrate 1 to lambda, right? Now, so the change of variable can be the function u of x equal to t of x, right? That's a continuous function, c1 and everything you want. Okay, so let that be our u. Yeah, then the change of variable formula tells me that I can move this back here. And then this set S, now I have to use the inverse image on the u, so I just get the set S. And now I'm integrating still the function 1. And here I put the determinant of the derivative of u, which is t, in this case, the lambda. Okay? And now this is determinant of t, Lebesgue measure of S, right? So that's actually the way I would prove that statement. So that was nice because it gives us an example of why of usefulness of the change of variable formula. All right, moving on with the general argument. Back to the other video. So now, what do we want to do? We take in this picture here, we're going to choose our E1 to be unit length in the direction of A. And then we're going to choose our E2 to be in the plane spanned by A1 and A2, but perpendicular to E1. And then E3 is going to be the same. So the Gram-Schmidt method or process on these guys, and I will tell you what that means. So we take E1 of length 1 such that A1 is equal to some number alpha 1 times E1. And then we take E2 such that A2 is in the span of E2. E2 is perpendicular to E1. I'm not writing that up, but I need the following formula. So then, if we can write this as a linear combination of E1 and E2, then it means that there are coefficients like this. But now we have a problem with the notation here because now there's one alpha 1 here and one alpha 1 there, and clearly they are not necessarily the same. So let me stick a 2 here to signify that this is A2, and then I stick a 1 here to signify that I'm dealing with A1, and then we continue like this, right? So E3 will be perpendicular to E1, E2, such that A3 is in the range, so we can write A3 as alpha 1, 3, E1 plus alpha 1, 2, 3, E2 plus alpha 3, 3, E3. Okay, and then we continue this. until we reach D. So what can we say about size here? So let me again paint this. So here's E1 and here's A1. So if we're in one dimension, the determinant is just this number A11. And okay, if E1 points in the opposite direction, that would be a negative number. If E1 points in the same direction as A1, it would be a positive number. So if you take the modulus on this A11, you get the size of A, or the one-dimensional volume, if you want. Now, here's A2. Okay. So then here's E2. It's easier, of course, to choose them so that you always have a positive coordinate in the projection here. That's not necessary. Okay, so then here is our alpha 2, 2. And then the projection down here is our alpha 1, 2. Yeah? So what's the volume now? Well, the volume, or in this case, two-dimensional case, the area is going to be the same as, A1, 2. Sorry, that's exactly what it's not. It's going to be the height times the base. So it's A11 times alpha 11 times alpha 2, 2, right? So here we have the data matrix, which consists of A1 and A2. If it's just two-dimensional, then this is alpha 1, 1 times alpha 2, 2. Okay, and in modulus to make sure you don't get negative numbers. Yeah? And then, of course, if I now add some sort of third vector here going out into the space, the only thing which is important is how high above do I get. And that's what this alpha 3, 3 is telling me, right? Where I put as long as I don't change alpha 3, 3, I can choose alpha 2, 3 and alpha 1, 3, put my tip of that anywhere, and it's not going to change the volume, right? So if I do this in 3D, here's the matrix with these three guys. It is alpha 1, 1 times alpha 2, 2 times alpha 3, 3, and so on. Now, what is the matrix A in this new basis? So technically, if you call these vectors, I already call them E1, E2, and if I make a matrix out of that, these guys as columns, I call that U, then this guy, what I'm looking at here is U, A, U minus 1, right? This is what I mean by the matrix A in this new basis. And it's going to be, here's alpha 1, 1, and then just zeros. Here's alpha 2, 1, alpha 2, 2, and then just zeros, and so on, right? Alpha 3, 1.
Let's swap the order of indices populated. Alpha 1, 2, alpha 1, 3, alpha 2, 3, alpha 3, 3, and then just zeros. Here's your alpha D, D.
Right? And we know from linear algebra that it's very easy to evaluate determinants of such matrices. You just multiply these numbers on the diagonal. So the determinant here is of this guy A, whether it's in the old or the new basis, is going to be alpha 1, 1 times alpha 2, 2, double dot alpha D, D. So that corresponds well with our intuitive idea, at least, of the volume of the parallelepiped spanned by the column vectors A1 up to AD. Good. Yes, now we establish that. So now let's get back to this situation and figure out more precisely why he pops up here. And I'll actually just erase here. Okay, let's say that now it is dry. So we have to do a zoom in on this situation here. So let's paint this box there again. So here's the set U, you know, and then here we have that box, right? So there is a small box. So here's a point X, right? So X1, X2, and so on. And here's a length, which we can call delta X1. Here's another length, which we can call delta X2, and so on. If we're in higher dimension, then delta X3 on the third axis, and so on. Okay, so this is being mapped to that small guy, but now we zoom in. So he's going to look something like this, right? Where here, which vector is this? It's going to be, okay, so let's write up what is the Taylor formula in several variables. It is U of X plus H. It's approximately equal to U of X plus, and then a sum. J goes from 1 to D. And here comes the partial derivatives, which are vectors, because U is a vector function. And here Hj, right? So approximately equal to, because I don't write the higher order terms. So now this guy, that's just a translation, right? If it's you move in space, so that doesn't change the volume. You know what Lebesgue measure is translation invariant. So if this base point here is U of X or just the origin, we don't care. So we can throw him away completely. We're just interested in knowing the size of this guy, and here I can put the origin, right? Then what is this vector? That's delta U delta X1 times, sorry, du dx1 times delta X1. This is a number, yeah, which gives the length. Similarly here, I have du dx2 times the length delta X2. And so on to higher dimensions. So now, yeah, this delta X has just rescaled the partial derivatives. So we actually get here very small vectors. And now the question is, what is the volume? Well, let's use more proper notation. So what's the Lebesgue measure of what's the Lebesgue measure? Okay, I'm going back to the improper. So the volume spanned by these vectors, so delta U1, delta X, sorry, not U1, delta X1, delta X1, dot, U dx d, delta X d, right? So here I have d vectors, they span some volume. So the Lebesgue measure of the corresponding, parallel epiped. We know by now that this is equal to the modulus of the determinant of the corresponding matrix. And now is the beauty that determinants are linear in each coordinate, in each column separately, meaning that here I have a column vector, okay? I multiply with a number, that number I can pull it out. Same here and same with all columns, right? So I pull out all these guys, and now I get delta X1
times delta X2 times delta XD, and then just the determinant of what's left here becomes the
derivative, right, of u. So here you kind of see it, right? If we're doing Riemann notation, sort of the Riemann integral that we're interested in, what's the size of this box? Well, it's this number here. And what's the size of this thing on the other side? Well, it's that number times this determinant. So then we really get a feeling for that's why it appears in the change of variable formula here. Yeah. So that's why it's an important number. So it has its own name. It's called the Jacobian. And usually it also has a notation. So people write JU for Jacobian of U. So that's not, yeah, that's the modulus of the determinant. That's what the Jacobian is. I'm not sure if the modulus is necessarily there or not, but anyway. It's a bit confusing in notation. Jacobi's matrix is sometimes this guy called, but the Jacobian is the determinant of that matrix, which is easier to just call it a derivative. Okay, so that ends somehow the soft introduction to this formula. Now starts the hardcore details. And let me sit down and think about them before I talk more.